Okay, so once we have a quantum computer, we want to run some quantum algorithm on it and get some interesting results. Okay, so in the previous couple of lectures, we talked about theoretically constructing ways of building a quantum computer using a bunch of 1 qubits and 2 qubits. Well, it's only a theoretical construct, but I was trying to argue that in principle you can do all the things that a quantum computer needs to do by performing a whole bunch of 1 qubit operations as well as 2 qubit operations. And that's as far as you will need to accomplish because essentially the higher qubit operations can be basically factorized in terms of 1 qubit and 2 qubit operations. So now we're going to assume that such a high performance quantum computer is already at our disposal and then start thinking about what can be done in a useful way by utilizing such a quantum computer. In other words, we want to talk about the quantum algorithms. And probably you have heard that the most famous instance of a quantum algorithm and most effective and powerful is the so-called Shor's algorithm. And Shor's algorithm is a way of factorizing a huge number, which is given as the product of two primes. So a simple example is a number 15, which is a product of two primes, 5 and 3, like that. And of course, this is simple, but if the number of digits in each prime reach to, let's say, 100, and you're only given this product, then it's nearly impossible to figure out exactly what were the original two primes which made up such a product. And this is a very challenging problem in both computer science and mathematics, a branch of mathematics known as the what is it? In Korean, it's called 정수론. Okay, so it's called number theory. And what Shor discovered theoretically was that if you had a quantum computer at your disposal, then factorizing a large number into their parent primes like this becomes exponentially easier. By easier, I mean it can be accomplished on a time scale that is exponentially faster than any classical computer. So that was a big revelation, and that revelation is what has led many people to actually serious thinking about quantum computer as a bias, as a viable discipline of a potentially new and very powerful science. Really, a lot of people jumped into the field because of Shor's algorithm, which came out around 1995. Okay, so this was a landmark paper, and actually, the Shor's algorithm involves a whole bunch of results borrowed from the number theory, as well as a clever understanding and the use of quantum mechanics in building this quantum factorization algorithm. And we're not going to cover the Shor's algorithm in its entirety because most of the argument involved in this algorithm is rather highly mathematical. And I would tend to think that this course is about the physics side of things rather than mathematical side of things of quantum computation. However, what I will discuss is an important tool, very important ingredient, I should say, in Shor's algorithm, known as the quantum Fourier transform. And of course, everyone knows what Fourier transform is. And the word quantum, the adjective, doesn't really add a whole lot of new mathematics to it. This adjective here is here mainly because the uh, the um, the algorithm of quantum Fourier transform is supposed to run on the quantum computer. So okay, I will explain that in a minute. But basically, the reason why it's called a quantum Fourier transform rather than an ordinary Fourier transform is because it presupposes the existence of a large scale and perfectly working quantum computer at your disposal. Okay? So I'm saying all these things because I don't want you to get scared by the formidable new vocabulary. You will see that there's actually nothing formidable about the mathematics side of it. Okay? But quantum Fourier transform is actually just an example of a broader class of concept called the quantum integral transform. Okay. Again, when you actually sit down and look at the mathematics of it, this is this is nothing new. But again, people use this fancy vocabulary because the whole assumption is that this algorithm is supposed to run on a quantum computer. Okay, so you put quantum in front of every word that you already know simply because the idea is to have it run on a quantum computer rather than a classical computer. Okay, so the basic assumption is that you have at your disposal a whole bunch of qubits. And I'm going to assume that there are n qubits in total. With n qubits, each qubit realizing a binary number 0 and 1, 0 and 1, the sort of number that this n qubit cluster can realize ranges from 0 all the way up to 2 to the n minus 1. And I'm going to use a capital N to denote this number 2 to the n because this number will show up frequently in our subsequent discussion. So actually what it says is the obvious statement that the dimension of this Hilbert space afforded by the n cubic cluster is exactly 2 to the n, or simply a capital N. Okay, and one way to think about the dimension of this Hilbert space is that it's capable of realizing integers that start from 0 and reach all the way out to capital N minus 1. Okay, that's just an obvious statement. Okay, and then I'm going to suppose that there exists a function. So this is just an ordinary function, which depends on these argument, and x is one of these numbers that can be realized by an n-qubit cluster. So x can be anywhere between 0 all the way up to 2 to the n minus 1, or capital N minus 1. And the key idea is that when you have a pretty large number of qubits that are put together, then this exponential number can be quite large, and therefore this capital N can be quite large, and therefore you can basically cook up a quantum computer that can manipulate a very large integer, and the function f, which depends on a set of very large number of integers. Okay, so the key idea actually is that that you assume that one is already capable of building a quantum computer having a large integer n, which means you put together a whole bunch of qubits in this manner, and hope that they're still maintaining a perfect quantum coherence, and everything is just working the way they're supposed to, etc. And actually, that's pretty far from reality. The most that people have been able to manage thus far is n equal to 50-ish, achieved by Google a couple of years ago, and I wouldn't say that n equal to 50 is necessarily a large number. So actually, to solve this factorization problem for these integers that are incapable of solving by a classical computer, to do that you actually need an n that is on the order of 10,000 or even 100,000, and we're obviously very, very far away from that goal or standard. Okay, well, anyway, even though the reality is still far away from us, we'll still press on with our theory. Well, because once you establish a good theory, then the theory cannot crumble under the test of time. So first of all, what is QIT? Well, the definition of a quantum integral transform is this thing. Okay, so that's it. Yeah, this is it. Well, actually, this definition alone has nothing to do with being quantum. Okay, you can pretty easily recognize that this is nothing but a matrix multiplication. Okay, because if you arrange all of these numbers, f of 0, f of 1, etc., as a column vector like this, then this thing which is called the kernel is obviously a matrix. So K00, K01, K0 n minus 1, K10, K11, all the way up to K1 n minus 1. And I'm going to show you what the final row would looks like. Kn minus 1, 0, Kn minus 1, 1, all the way up to Kn minus 1 and minus 1. And now this kernel matrix would multiply the input column vector f0, f1, all the way down to f of n minus 1. Okay? Well, so this is nothing but a familiar matrix multiplication where the input vector is designated as a small f, and the output vector is designated as a capital F, and the mapping from a input vector to an output vector in this sort of hypothetical vector space is implemented by this matrix K. Okay, in other words, this is nothing but a simple matrix multiplication that we have known all along. So why is this called quantum? Well, because we are basically assuming that this entire multiplication process is going to take place on a bunch of quantum chips or quantum qubits. Okay, so the mathematics is not quantum at all, but the idea is that this mathematical manipulation will be performed not by a classical computer but a quantum computer. Okay, that's why we put quantum in front of every word we use. And in particular, the kind of kernel matrices that we will be interested in is going to be unitary. Unitary. Why are we particularly interested in the unitary matrix or unitary kernels? The reason, I will give you the reason in a minute. But first of all, let me prove this important theorem that once you have this quantum integral transform relation between one vector, small f, and another vector, large F, then its inverse relation can also be easily constructed. And the kernel matrix that needs to be involved in this inverse transformation is just the Hermitian conjugate of the kernel matrix. Okay, normally here you would need to have the inverse of the K matrix, but since by assumption this is a unitary matrix, the inverse matrix is equal to the Hermitian conjugate matrix, and that's why we're free to use this Hermitian conjugate matrix as the kernel to perform the inverse map from the capital F to a lowercase f, and this is the map from the lowercase f to the capital F. Okay, so in this hypothetical vector space, I have this one element in the vector space which goes into the other element of the vector space called the capital F through the mapping by the K matrix or K kernel, and the inverse transformation is afforded by its inverse, or since K is supposed to be unitary, it's afforded by its Hermitian conjugate. Okay, so I'm going to perform a simple and well-known proof that indeed these mappings are as they should B. Uh, and I'm going to prove it by doing the following thing. So I'm going to start with this definition, and then I'm going to insert this other definition into the capital F over here and just see what happens. Okay. So obviously now we're going to have a double summation because f of y is an expression which involves another summation. And I'm going to use z rather than x because x is already used up here. So the expression will be like that. Okay. And I can rearrange the summation procedure. Okay. And then realize that this is nothing but just a matrix multiplication of K dagger matrix with the K matrix. And all I'm doing is to check out the elements of this product matrix with indices x and y. But since K dagger K is just a unity matrix, these matrix element better be the canonical delta. And I'm going to write down the canonical delta in this way. Sorry, this should be z, and this should be z as well. Okay, so after performing this matrix multiplication, I end up with this nice and simple canonical delta function, which eliminates the summation over the z and simply gives me the f of x, which is what I had initially on the left-hand side of the equality. So therefore, the mathematics all checks out. And that's pretty nice. Okay, so what is a quantum Fourier transform? Quantum Fourier transform is a special case of this quantum integral transform where this kernel is given by this simple function. Okay. I should not forget this factor, normalization factor. And omega is the nth root of unity, so to speak. Okay, so omega to the nth power is 1. And recall that n was this huge, exponentially huge number, 2 to the little n, where little n stands for the number of qubits that have been put together into a quantum computer. Okay, so if you like the more explicit version of the kernel, then I can give you that in this form. Okay, so that would be my kernel. Okay, so is this really unitary? Because I mentioned that we will only take interest in the sort of quantum integral transforms that are conducted by a unitary matrix serving as the kernel. So is that the case with this special choice? Well, that's easy to verify, so I'm going to verify it. So I'm going to do this summation. and prove that what results is an identity. So what is K dagger XY? K dagger XY is KYX, Hermitian conjugate, complex conjugate. But you can see that this matrix element is symmetric under the interchange of X and Y. So this is actually just the complex conjugation then. And since omega complex conjugate is omega inverse, you realize that this is just omega to the plus xy power. Okay, good. So now I'll just plug in the results. This first factor gives me e of plus omega xy. And this second factor gives me omega to the minus yz. Okay, then I'm going to write down this same thing in a more explicit way. E to the 2 pi I over n y x minus c. Okay. So hopefully this expression is familiar to you. This is what's called the discrete Fourier transform or something like that. And I hope that I don't have to go through the mathematics of this expression again. I will just simply quote the results. The result is the critical delta function. That is, if these two arguments were equal, then you would get a nice identity. You would get 1. But if x and z were unequal, then you would get 0 because this is basically a phase factor. And when x and z are not equal, then these phase factors would tend to cancel each other out and give you 0. Okay, so this is the desired result. So the bottom line is that if I choose the elements of my unitary matrix in this way, then indeed the product of the K dagger with K becomes the identity. So therefore K is a unitary matrix. Okay. And so in the next lecture, I'm going to use this quantum Fourier transform to do some useful tricks. And just give you a heads up, it's called the period finding. And another theme I'm going to touch upon is that of finding the eigenstate of some quantum Hamiltonian. And in case you have been following the literature somehow, you may have encountered this acronym, variational quantum eigensolver. So what happens is that people, we are all scientists, are also humans, so they tend to want to elevate the novelty or the importance of what they do. So one of the ways in which they accomplish that is by giving fancy names to what they do. Okay, and VQE is just a fancy vocabulary that people cooked up for this algorithm to find the eigenstate of the Hamiltonian. This is potentially a very useful algorithm and definitely worth knowing about. And it's heavily based on this idea of a quantum Fourier transform. Okay, so that's the that's a little heads up on what's forthcoming in the next lecture or two.